Hi, everyone. We're continuing with lesson 23 on normal approximations to binomial distributions. We're saying that these normal approximations apply under these conditions when NP and NQ are at least 5, where Q is 1 minus P. N, remember, is the number of trials. P is the success probability per trial. Q is the failure probability per trial. So for example, N could be the number of flips of a coin, P is the probability of heads per flip, Q is the probability of tails per flip. Now both these conditions favor a normal approximation because larger values of N tend to favor a normal approximation, and values of P and Q that are not close to 0 will also favor a normal approximation. So of these binomial distributions or histograms, the one that really does count is this one over here. N equals 10, P equals 1/2. This is the one binomial distribution of these 50 for which the normal approximation will apply, because NP and NQ are 5. Now, on top of these defining parameters for the binomial, N and P, we also care about the mean and standard deviation. So the mean and standard deviation are two more parameters for the binomial distribution that we care about, and we're also going to need those values for their normal approximations. So what are the formulas for the mean and standard dev of a binomial distribution? Well, from probability and algebra, we get that the mean mu is given by n times p, which makes sense because, for example, if you flip a fair coin 10 times, if n is 10 and p is 1/2, then the expected value is 5 heads. That's no surprise. The standard deviation, sigma, is given by the square root of npq, where, again, q is 1 minus p. It's the failure probability per trial. In this case, the probability of a tail. Now, it makes sense that if we want to approximate this binomial NP distribution, then if these conditions apply, if NP and NQ are at least 5, as we said before, then we're going to say that X can be approximated by a normal distribution with these parameters, the same parameters as for the binomial distribution that it's approximating. That makes sense. We're going to use a normal approximation where the mean mu is NP, same as for the binomial, and the standard dev sigma is root NPQ, same as for the binomial. Okay. Now, when we approximate a binomial distribution by a normal, there's another issue. It's the fact that we're approximating a discrete distribution, a binomial, with a continuous distribution, a normal, and that leads to some awkwardness. So to adjust for that awkwardness, we're going to apply continuity corrections. Maybe not later in this course, but for right now, as we're focused on probability, we're going to try to make our estimates more precise. So we're going to apply continuity corrections. Continuity corrections are used to adjust for the fact that we are using a continuous distribution, in this case, a normal distribution, to approximate a discrete distribution, in this case, a binomial distribution. We're using a normal to approximate a binomial, a continuous distribution to approximate a discrete distribution. So a discrete distribution gives us bars in a probability histogram. A continuous distribution gives us these curves, these density curves, and there's going to be some awkwardness. So for example, let's say that we let X be the number of heads when a fair coin is flipped 100 times. Let X be the number of heads when a fair coin is flipped 100 times. X will then have this corresponding binomial distribution, where n equals 100, the number of flips or trials, and p equals 1/2, the probability of heads is 1/2, by definition of a fair coin. Now let's say that a friend of ours is going to flip a fair coin 100 times. Well, and I win a bet with my friend if the coin comes up heads between 45 and 55 times inclusive, meaning that I win the bet if my friend gets exactly 45 heads. Also, I win the bet if my friend gets exactly 55 heads, or if my friend gets any number in between, 46, 47, and so forth. I want to find the probability that I win this bet, that the number of heads will be between 45 and 55 inclusive, including these numbers of heads at the boundaries. Now, later on, we're going to find z-scores for boundary values, but I need to nudge these a bit because I want to apply continuity corrections. So here's the idea. We associate the integer value a, such as 45 or 55, in the binomial distribution with the interval of real numbers from a minus a half to a plus a half. Basically, these are the real numbers that round off to a when we do our approximating normal distribution, and we're going to think rounding. Let's do some examples of that. In particular, what are the real numbers that round off to 45 to the nearest integer, and what are the real numbers that round off to 55 to the nearest integer? Bottom line. What are the real numbers that correspond to the integer 45 from the discrete binomial distribution? It's this interval of values over here, this range of values over here. What are the real numbers that round off to 45 to the nearest integer? It's the interval from 44.5 to 45.5. To get these goalposts, these fence posts, I take 45, I subtract 1/2 or 0.5 to get the 44.5, and I add 0.5, I add 1/2 to get the 45.5. And that's true for any integer. When we go from the binomial to a normal approximation, I take the integer of interest, I subtract 0.5 for the left fence post, and I add 0.5 for the right fence post. Likewise, for the integer 55 for the binomial distribution, well, what's the interval that corresponds to that? Actually, I'll use blue for this. What real numbers round off to 55? The real numbers from 54.5 to 55.5. Now, I realize that technically 55.5 rounds up to 56, but that's the best we can do. Bottom line, this interval, this block of real numbers in here, will round off to 55, just as this block of real numbers over here will round off to 45. Now, this shaded region inside here corresponds to the values for our normal distribution where I win my bet. Well, of course, I win for 46 heads, 47 heads, and so forth, but I also win for exactly 45 heads, meaning this block, so I shade this in. And I also win for exactly 55 heads, meaning this block, so I shade this in. I win if the coin comes up heads exactly 45 times, or for that matter, exactly 55 times. So I shade in both these boundary blocks, which means where are our actual goalposts when we convert to z-scores? What are the boundaries for this shaded region over here? We go all the way from 44.5 over here. I'll put this in purple actually. We have to go all the way from 44.5 over here as our left goalpost to 55.5 over here as our right goalpost. And the shaded region that we want is everything in between. Okay, so to approximate the probability that the number of heads is between 45 and 55 heads inclusive, we actually want the probability that corrected x for a normal approximation will be between 44.5 and 55.5. And in fact, at this stage, the bars won't matter because we're dealing with a normal distribution, a continuous distribution. Normals are continuous. Normals are continuous. So we don't care about the bar so much. For discrete distributions like binomials, we can care about the bars. Here we do. But by the time we get to normal, we don't care about the bars anymore. And again, why are we doing this? Why are we performing these continuity corrections? Well, for example, why do we replace the 45 here with the 44.5? Because if we take a z-score for the 45, then what's happening? Well, really, we're supposed to consider this corresponding binomial bar, this binomial bar here, when we consider adding these various probabilities for the binomial. But if you take 45 as your boundary z-score, if we took the z-score for 45 as our boundary, what happens? We're going to cut this boundary bar in half, and we're going to lose this probability mass over here, which means we're going to be a bit off. Now, again, continuity corrections will not bother us later in the semester, but if we want to be as accurate as we can, we want to get this piece of bar, which means that we prefer the 44.5 as our true boundary for the normal as opposed to 45. Likewise, we prefer 55.5 to 55 because we want this extra piece of bar. This extra piece of bar over here, which really is supposed to count. All right, next up, we're going to do an example. And in particular, we're going to find this probability.